On a warm afternoon in the summer of 1950, the physicist Enrico Fermi sat down to lunch at the Los Alamos National Laboratory in New Mexico with a group of colleagues that included Edward Teller, Herbert York, and Emil Konopinski. The conversation had turned, as it sometimes did among physicists who had spent years thinking about enormous questions, to the recent wave of UFO sightings that had been appearing in American newspapers. Fermi was known for his ability to arrive at quantitative estimates for seemingly impossible questions through a series of simple logical steps, the kind of reasoning now called a Fermi estimation. At some point during the meal, apparently out of nowhere, he looked up from his plate and asked, "But where is everybody?" The question was not about the UFOs specifically. It was about the universe itself. His colleagues understood immediately what he meant. The universe is approximately 13.8 billion years old. It contains an estimated 2 trillion galaxies. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. The majority of those stars, we now know, have planets orbiting them. Given billions of years of opportunity and billions of candidate locations, the emergence of intelligent life capable of technology and communication should, by any reasonable probability estimate, have happened many times over. If even a tiny fraction of those civilizations developed radio communication and then space travel, the Milky Way should have been colonized, or at least contacted long ago. The evidence of other civilizations should be everywhere, and yet nothing. The sky is silent. The question haunts science to this day. What Fermi was describing in his casual lunchtime remark was a logical contradiction at the heart of our understanding of the universe. On one side, the sheer scale of space and time makes it seem almost statistically inevitable that other intelligent species exist or have existed. On the other side, after decades of searching with increasingly sensitive instruments across radio, optical, and infrared wavelengths, we have detected nothing that requires extraterrestrial intelligence as an explanation. Not one unambiguous signal, not one artifact, not one visitor, past or present. The absence is as striking as the expectation. The contradiction between what we expect and what we observe is what makes this a paradox, and it is one of the most profound unresolved questions in all of science. It is worth being precise about what the Fermi Paradox is not. It is not a claim that extraterrestrial life definitely does not exist. It is not a claim that we have looked everywhere and found nothing. We have searched a tiny fraction of the sky at a limited range of frequencies for a short period of time relative to the age of the universe. What the paradox does claim is that given how old the universe is, given how common planets appear to be, given how long life has had to evolve and civilizations have had to develop and spread, the silence is deeply surprising. It demands an explanation, and the various explanations proposed by scientists over the past 70 years say very different things about the nature of life, the nature of intelligence, and the long-term prospects for our own civilization. The title of this documentary contains a promise. The Fermi Paradox has a beautiful answer. That is not a claim that the answer is comforting in every sense, or that it resolves all uncertainty. Some of the proposed explanations are sobering, some are genuinely frightening, but woven through all of them, if you look carefully, is something worth sitting with, something that changes how you understand your own existence and the significance of this small planet at the edge of an ordinary galaxy. We are going to earn that answer by working through the full problem. We begin with what the Fermi Paradox actually is, in precise scientific terms, then the Drake equation, then the silence itself, then the great filter, then the alternative explanations, and then the answer that I find most beautiful. Over the 76 years since that New Mexico lunch, The Fermi Paradox has evolved from a casual observation into a serious scientific research program. Physicists, astronomers, biologists, and philosophers have written hundreds of peer-reviewed papers exploring its implications. The search for extraterrestrial intelligence, known as SETI, has operated continuous listening programs since 1960. The Breakthrough Listen initiative, funded at $100 million for 10 years beginning in 2015, has surveyed millions of stars with the most sensitive equipment ever applied to the question. Astrobiology has emerged as a discipline dedicated to understanding where life can arise and how complex it can become. None of this has produced a confirmed detection. The silence continues, and its continuation becomes more significant every year. The Fermi Paradox has attracted attention not just from astronomers and physicists, but from biologists, philosophers, economists, and policymakers. Anyone who takes seriously the question of humanity's long-term place in the universe. It sits at the intersection of several of the deepest questions available to science. Is life rare or common? Is intelligence an inevitable product of evolution or an accident? Does civilization tend towards survival or self-destruction? Are we early in cosmic history or late? Each of these questions would be profound on its own. The Fermi Paradox binds them together into a single question that can be asked in 4 words. And the fact that we do not have a confident answer 76 years after Fermi asked it at a lunch table is itself a significant piece of information about the state of our knowledge. Settle in. The universe is 13.8 billion years old. You have been here for a fraction of a cosmic second. Tonight, in the quiet, we ask the question that has no comfortable answer and see where it leads. Where is everybody? The search begins now. The Fermi Paradox is not, strictly speaking, a paradox in the logical sense of a statement that contradicts itself. It is what philosophers of science call a Fermi question, an argument by apparent contradiction between a strong prior expectation and an observed fact. The expectation is that intelligent life should be common. The observed fact is that we have detected none. The tension between these two things is the paradox, and like all good scientific tensions, it cannot be dissolved by simply wishing one side away. Both sides are based on real reasoning from real evidence. The question is which reasoning has a flaw, or whether both are correct and the resolution lies elsewhere. The prior expectation rests on 2 pillars. The first is the age of the universe. At 13.8 billion years old, the cosmos has had more than twice as long as Earth has existed to produce habitable planets. Allow chemistry to organize into life. Allow life to evolve into complex forms, and allow complex life to develop intelligence and technology. If the process that produced us required 4 billion years, and if the universe is nearly 3.5 times as old as the solar system, then civilizations that arose before ours could be billions of years more technologically advanced. A civilization with a billion-year head start could have reshaped the galaxy so thoroughly that its presence would be obvious even across intergalactic distances. The second pillar is the number of candidate locations. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Data from the Kepler Space Telescope mission, completed in 2018, established that on average there is at least 1 planet for every star in the galaxy, and likely closer to 2 or 3. The fraction of these planets in the habitable zone of their star, the range of distances where liquid water can exist on the surface, is estimated between about 20 and 40% for Sun-like stars. Even applying very conservative assumptions at every step, the number of planets that have had the ingredients for life at some point in their history runs into the billions for the Milky Way alone. and into the trillions for the observable universe. The argument for detectability rests on a principle from computer science and game theory. If a civilization can expand, it will. A species that develops interstellar travel and has access to abundant energy and resources has every incentive to colonize available systems. At even a modest fraction of the speed of light, a civilization could spread across the entire Milky Way in 10 to 100 million years. A very short time relative to the age of the galaxy. If any civilization capable of space travel arose even 500 million years ago, the galaxy should by now be fully colonized or at minimum surveyed. The absence of any evidence for this is the central puzzle. The argument extends to communication. Even a civilization that never leaves its home star system could make its presence known across vast distances. A sufficiently powerful radio transmitter aimed at likely targets could be detected across the galaxy with instruments not much more advanced than our own. Artificial signals, structured, non-random, clearly designed, would stand out immediately against the noise of natural astrophysical sources. Continuous monitoring of the radio sky since 1960 has yielded no confirmed unambiguous signal of artificial origin. The sky, at every frequency we have examined, appears natural. This is not what you would expect if technological civilizations are common. It is important to understand what absence of evidence means here. In everyday life, absence of evidence is often not evidence of absence. If you look for your keys briefly in one room and don't find them, that doesn't mean they don't exist. But absence of evidence does become evidence of absence as the search becomes more comprehensive. 60 years of radio monitoring, covering large portions of the sky at many frequencies, has provided no detection. The WOW signal of 1977, the one apparently anomalous detection in all those years of observation, was never repeated despite hundreds of follow-up observations of the same sky location. The comprehensive nature of the search, while not exhaustive, is substantial enough that the silence is meaningful. One of the most compelling formulations of the paradox came from physicist Michael Hart in a 1975 paper in the Quarterly Journal of the Royal Astronomical Society. Hart argued that the absence of extraterrestrials on Earth is by itself a significant observational fact. If any spacefaring civilization existed anywhere in the Milky Way in the last several hundred million years, it should have reached Earth by now through either direct colonization or the spread of automated probes. Earth is an appealing destination. It has liquid water, a thick atmosphere, abundant organic chemistry. The fact that we find no alien presence, no artifacts, no structures, no biological evidence of any prior occupation, is a constraint that any theory of extraterrestrial life must explain. Hart called this fact A. It is the empirical foundation of the paradox. The physicist David Brin extended this analysis in a 1983 survey paper that catalogued the proposed solutions to the Fermi Paradox. Systematically for the first time, Brin divided solutions into two broad categories. Category 1, they exist, but we have not detected them for one reason or another. Category 2, they do not exist, or do not exist anywhere close enough to have reached us. Both categories contain multiple sub-hypotheses, and several of the most interesting ones fall in between. The taxonomy has been refined and extended in the decades since, but the basic structure remains the same. In the chapters that follow, we will work through the most scientifically serious proposals in each category, beginning with the mathematical framework that makes the question precise. What gives the Fermi paradox its particular weight is not the absence of radio signals. It is the absence of any evidence at all. We have mapped the cosmic microwave background and found no energy anomalies that require engineering to explain. We have observed hundreds of thousands of stars and found no megastructures, objects like Dyson spheres, that would capture a star's entire energy output and make it thermodynamically distinctive. We have found no evidence of large-scale astroengineering anywhere in the observable universe. If even one civilization in the history of the cosmos had undergone indefinite exponential growth and spread, we might expect the universe to look quite different from what we see. It does not look different. It looks natural all the way down. The Fermi Paradox is ultimately a question about probability, history, and the nature of life and intelligence. It asks us to look at our own existence clearly and ask whether we are typical or unusual, whether intelligence is an inevitable product of evolution given enough time or an extraordinarily rare accident, whether civilizations tend to flourish and spread, or whether something always stops them. These are not questions we can answer from armchairs. They require evidence, and the evidence we have is the silence. That silence is one of the most data-rich non-detections in the history of science. How to read it is the task of this documentary. Before we explore proposed explanations, we need the mathematical framework that makes the question precise. Frank Drake, the astronomer who launched the first formal SETI program, and who spent his career searching for signals from other civilizations, gave us that framework in 1961. He wrote it on a blackboard. It has been on blackboards and in textbooks and in scientific papers ever since. It is called the Drake equation, and it is the tool that turns the Fermi Paradox from a philosophical puzzle into a quantitative scientific problem. It is the subject of the next chapter. In November of 1961, 11 scientists met at the National Radio Astronomy Observatory in Green Bank, West Virginia, for the first formal scientific conference on the search for extraterrestrial intelligence. The meeting was organized by Frank Drake, a young radio astronomer who had already conducted the first systematic radio search for extraterrestrial signals, Project Ozma, earlier that year. To give the conference a shared framework for thinking about the problem, Drake wrote an equation on a blackboard. He had not intended it as a permanent contribution to science. It was a meeting agenda, a way of organizing what the attendees knew and didn't know. But the Drake equation, as it became known, has structured the scientific conversation about the Fermi Paradox ever since. The equation estimates the number n of technologically advanced civilizations in the Milky Way currently capable of electromagnetic communication. It does this by multiplying together 7 factors, each representing one step in the chain from star formation to communicating civilization. The equation is n equals r star multiplied by fp multiplied by ne multiplied by fl multiplied by fi multiplied by fc multiplied by l. Each term represents a probability or rate, and their product gives the estimated number of civilizations. Drake's insight was that no one could estimate n directly, but each factor might be estimated separately as data accumulated, and those estimates could then be combined. The equation does not solve the Fermi paradox, it maps it. The first term, r star, is the average rate of star formation in the Milky Way per year. In Drake's time, this was poorly known. Today, based on decades of infrared and radio astronomy, it is estimated at approximately 1 to 3 new stars per year in the Milky Way, averaged over its history. This is now the best constrained term in the equation, the one where scientific consensus is strongest. The uncertainty is small relative to the other terms, and the value is robust against different measurement approaches. The Milky Way has been forming stars for approximately 10 billion years, and the current rate, while lower than it was in the early universe, gives a large cumulative pool of candidate stellar systems. The second term, FP, is the fraction of stars that have planetary systems. When Drake wrote the equation, we had detected 0 exoplanets. The existence of other solar systems was plausible but unconfirmed. The Kepler Space Telescope mission transformed this completely. By monitoring 150,000 stars for 4 years and detecting the tiny dips in brightness caused by planets transiting in front of their host stars, Kepler established that virtually every star has at least one planet. FP is now estimated very close to 1. Approximately 100% of stars have planets. This is the second best constrained term in the equation, and the one that has changed most dramatically from Drake's time. The third term, NE, is the average number of planets per star system that could support life. Planets in the habitable zone where liquid water can exist on the surface. This is less well constrained than the first two terms. But Kepler data combined with radial velocity surveys suggests that roughly 20 to 40% of Sun-like stars have a planet in the habitable zone. For red dwarf stars, which are more common, the fraction is also significant, though the habitability of their planets is complicated by factors like tidal locking and stellar flare activity. The number of potentially habitable planets in the Milky Way is estimated in the range of tens to hundreds of billions. The fourth term, FL, is the fraction of habitable planets where life actually develops. This is where the equation's uncertainty explodes. We have exactly one example, Earth, and we do not know whether the origin of life on Earth was a near inevitable consequence of chemistry in the right conditions, or an extraordinarily rare event that required a specific improbable sequence of molecular accidents. Estimates for FL range from essentially 1, life is nearly inevitable on any sufficiently wet, warm, rocky planet, to something vanishingly small. The detection of life on Mars, or in the ocean of Enceladus, or in the atmosphere of Venus, would provide a second data point that would dramatically change our estimate of this term. Until then, it remains the deepest unknown in the equation. The fifth term, Fi, is the fraction of life-bearing planets where intelligence eventually develops. Intelligence is not the inevitable product of evolution. It is one of many possible successful strategies among organisms competing for survival, and it is expensive to maintain. For hundreds of millions of years, life on Earth was entirely microbial. Multicellular organisms arose relatively late. Intelligence of the human kind, capable of abstract reasoning, cumulative culture, and technology, appears to have arisen only once in 4 billion years of terrestrial evolution. This suggests that intelligence may be rare even on planets where life exists, though our sample size of one makes it impossible to assess the probability quantitatively. The sixth term, FC, is the fraction of intelligent civilizations that develop detectable technology and choose to communicate. This too is uncertain. A civilization might be intelligent without developing radio technology. It might take a path analogous to dolphins, who are highly intelligent but never developed tool use toward industrialization. Or it might develop technology but choose not to transmit signals into space, judging silence to be safer. The reasoning behind what the cosmologist Liu Cixin turned into the dark forest theory. Or it might communicate in ways we cannot yet recognize or are not yet looking for. The assumption that a technological civilization will broadcast recognizable radio signals is itself a significant and possibly wrong assumption. The seventh and final term, L, is the average lifespan of a communicating civilization, the length of time during which it is both capable of and actively engaged in detectable electromagnetic communication. This is perhaps the most frightening term in the equation. A civilization that destroys itself through war, environmental collapse, or technological accident shortly after developing radio might have L of only a few hundred years. A civilization that survives and flourishes might communicate for millions or billions of years. The value of L determines whether the galaxy is full of simultaneous civilizations or scattered with extinct ones. Drake himself estimated L at 10,000 years as a cautious optimistic case. Some researchers believe it may be much shorter. When Drake presented the equation at Green Bank in 1961, the assembled scientists, who included Carl Sagan, Philip Morrison, and John Lilly, arrived at a range of estimates for N between about 1,000 and 100 million, communicating civilizations in the Milky Way. This optimistic range reflected the fact that most of the scientists in the room were biologists or astronomers who believed life was common. More recent estimates, incorporating the additional constraints from astrobiology and the failure to detect signals, tend to be more conservative. But the remarkable fact is that reasonable values for each term produce N greater than 1 even when being quite conservative, which makes the silence all the more puzzling. Frank. Drake died in September of 2022, having spent 62 years searching for signals from other civilizations without finding one. He did not consider this a failure. He considered it work in progress. The equation he wrote on a blackboard in 1961 structured the entire field of astrobiology and SETI. It sits at the entrance to the question. Every piece of evidence about exoplanets, about the origin of life, about the evolution of intelligence, and about the detection or non-detection of signals fits somewhere into its 7 terms. The universe has not yet told us what N is, but the search for the answer has changed what we know about ourselves. In the spring of 1960, Frank Drake pointed an 85-foot radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened. He chose a frequency near the hydrogen line, 21 centimeters, on the reasoning that hydrogen is the most abundant element in the universe, and any technologically sophisticated civilization would recognize this frequency as a natural meeting point for interstellar communication. He listened for 2 months. He heard natural radio noise from both stars and one false alarm. A strong signal that turned out to be interference from a military aircraft. He called the program Project Ozma, after the Queen of the Land of Oz, chosen for its association with a faraway exotic place difficult to reach. He found nothing, but he had established the method. In the 65 years since Project Ozma, SETI programs of various scales and ambitions have monitored large portions of the radio sky at many frequencies. Surveys using the Arecibo telescope in Puerto Rico, the largest filled aperture radio telescope ever built at 305 meters in diameter, have covered millions of stars. The Green Bank telescope in West Virginia and the Parkes telescope in Australia have contributed data. Automated systems have scanned billions of radio frequency channels simultaneously using digital signal processing techniques that Drake could not have imagined in 1960. The total number of star systems surveyed in a comprehensive way is in the millions. The total number with convincing artificial signals detected, 0. The one exception, the one moment that briefly appeared to break the silence, came on the night of the 15th of August, 1977. Jerry Amon, a volunteer working on a SETI program at the Ohio State University Big Ear Radio Telescope, was reviewing computer printouts of the previous night's sky scan. One sequence of characters stopped him. The intensity of a narrowband signal at the hydrogen line frequency had risen sharply, peaked at 30 times the background noise level, and then decreased again, exactly as you would expect from a point source passing through the telescope's beam. Amon circled the characters, and wrote one word in the margin: wow. The wow signal, as it became known, has never been detected again, despite hundreds of subsequent observations of the same part of the sky. Its origin is still unknown. The wow signal remains the most tantalizing data point in 60 years of SETI. It had the right frequency, near the hydrogen line. It had the right duration, consistent with a point source tracked by a rotating Earth. It had the right intensity profile. It was unlike any known natural astrophysical source, but it was detected only once, on a single telescope with no simultaneous confirmation from a second instrument, and it has never recurred. SETI scientists treat it as a strong candidate for something interesting but impossible to classify without a repeat detection. It may have been interference. It may have been a natural but rare transient phenomenon. It may have been exactly what it looked like. Without a second detection, we cannot know. The silence that followed the wow signal is, in its own way, its most important feature. SETI's listening strategy has evolved considerably since the 1960s. The original focus on radio waves at the hydrogen line was rational but limiting. A civilization communicating via radio might use any of a vast number of frequencies. The frequency space to search is enormous. Over 10 gigahertz of bandwidth across the microwave quiet window, multiplied by billions of candidate stars, multiplied by uncertainties about the direction, timing and modulation scheme of any signal. The development of digital back-end systems capable of processing millions of channels simultaneously has expanded the searchable space dramatically, but the total space remains orders of magnitude larger than what has been covered. The search is comprehensive relative to what we could do decades ago, and still tiny relative to the total possible search space. Beyond radio, SETI researchers have explored optical and near-infrared wavelengths for signals, laser pulses or continuous laser beams that might encode information or simply signal presence. Pulsed optical CT programs have monitored thousands of stars for nanosecond flashes of laser light that would outshine the host star briefly. A sufficiently powerful laser aimed at our solar system could be detected with existing telescopes. Optical SETI has found nothing anomalous. More recently, researchers have explored the possibility of detecting technosignatures, physical signatures of technology, in stellar spectra, including the chemical signatures of industrial pollution in the atmosphere of a planet. Detectable in principle with the James Webb Space Telescope, KIC 8462852, known informally as Tabby's star after citizen scientist Tabitha Boyajian, who drew attention to its strange behavior, produced one of the most discussed potential technosignature candidates of the recent decade. The star shows dramatic and irregular dips in brightness, sometimes losing 20% of its light for days at a time, unlike anything produced by a transiting planet or any known natural astrophysical process. One hypothesis proposed in the media, though not the scientific consensus, was that the dimming could be caused by a partial Dyson swarm, a collection of structures built around the star to harvest its energy. Subsequent observations, particularly in ultraviolet wavelengths, suggested that dust, either from a disintegrating comet family or a disrupted planetesimal, provides a better natural explanation. The technosignature hypothesis was not confirmed, but the episode illustrated the value of looking for anomalies. The Breakthrough Listen initiative, announced in July 2015 by physicist Stephen Hawking and Russian entrepreneur Yuri Milner, allocated $100 million over 10 years to the most comprehensive SETI program ever funded. Using the Greenbank Telescope, the Parkes Telescope, and the Meerkat Array in South Africa, Breakthrough Listen has surveyed the 1 million nearest stars, 100 nearby galaxies, and the entire galactic plane at multiple frequencies. It has published its data openly, enabling independent analysis. It has found no confirmed artificial signals. The initiative continues, and its data archive represents the most complete publicly available SETI dataset in history. Fast radio bursts represent a genuinely puzzling class of transient radio phenomenon first detected in 2007 and still not fully understood. These are brief, extremely bright bursts of radio energy lasting milliseconds, originating from extragalactic distances, sometimes billions of light years away. Their energy is enormous. The most powerful known fast radio burst released more energy in a millisecond than the Sun emits in 3 days. Initially, their cause was completely unknown, and some researchers noted that an artificial origin could not be ruled out. The discovery of a repeating fast radio burst source and the eventual association of some with magnetars, highly magnetized neutron stars, has provided natural explanations for most, though the diversity of the population suggests multiple source types may exist. The absence of detectable megastructures is perhaps as significant as the absence of signals. A Kardashev Type II civilization, one that harnesses the total energy output of its home star, would be detectable thermodynamically. A star completely surrounded by a Dyson sphere or swarm would radiate its energy as infrared heat rather than visible light, and would be detectable in infrared surveys as a star-shaped infrared excess with no corresponding visible source. A survey of the WISE infrared satellite data examining millions of stars found some with anomalous infrared excesses, but all have been explained by natural sources such as warm dust disks. No confirmed Dyson sphere candidates exist in the current literature. The universe shows no signs of large-scale astroengineering anywhere in the observable volume. The silence, taken as a whole, is a scientific result. It is not a null result in the dismissive sense, the sense in which a failed experiment tells us nothing. It is a positive constraint on the space of possible answers. It tells us that if other civilizations exist, they are either rare, or distant, or quiet, or communicating in ways we cannot yet detect, or not communicating at all. Probably some combination. Each year of continued silence narrows the space of viable explanations. Understanding which explanations survive the constraint of the silence is the task of the next several chapters. We begin with the one that many scientists find most frightening. In 1998, the economist and futurist Robin Hanson published a paper titled The Great Filter. Are we almost past it? The paper proposed that somewhere in the chain of steps from the formation of a planet to the emergence of a star-faring civilization, there is at least one step so improbable, or so destructive when reached, that almost no planet ever makes it all the way through. Hansen called this improbable step or cluster of steps the Great Filter. The name has stuck because it captures the essential logic. Something filters out potential civilizations before they can fill the galaxy. The Fermi Paradox tells us the filter is real. What we do not know is where it falls in the sequence. The structure of Hansen's argument is elegant. If we are alone or nearly alone in the universe, and if the universe has had billions of years for life to arise and spread, then something must be preventing civilizations from developing or from persisting long enough to colonize the galaxy. That something is the Great Filter. The critical question is whether the filter lies mostly in our past or mostly in our future. If it is in our past, if humanity has already passed through the improbable step, then we may be genuinely rare, but have a promising future ahead of us. If it is in our future, if there is something that typically destroys or stops civilizations after they reach our level of development, then, humanity faces a catastrophic challenge that most civilizations have not survived. The most commonly cited candidate for the Great Filter in our past is the origin of life itself, abiogenesis. We do not understand how the first self-replicating molecules arose from non-living chemistry. The process may have been straightforward given the right conditions, in which case it happens on every suitable planet and the filter must lie elsewhere. Or the process may have required an extraordinary sequence of unlikely chemical accidents, in which case it may have occurred only once in the Milky Way's history, here on Earth. The fact that life appears to have arisen on Earth within a few 100 million years of the planet's formation is consistent with both interpretations. It either happened quickly because it was easy, or it happened quickly because any planet where it didn't happen within a billion years never had a chance to produce observers who could note the timing a second. Candidate for the Great Filter in our past is the transition from simple prokaryotic cells, bacteria and archaea, to complex eukaryotic cells containing a nucleus and membrane-bound organelles. This transition, which occurred on Earth approximately 1.5 to 2 billion years ago, appears to have required an extraordinary symbiotic event, one prokaryote engulfing another and forming a stable partnership. The mitochondrion, the energy-producing organelle in every eukaryotic cell, is a captured bacterium that retained its own genetic material. This event, the endosymbiotic origin of mitochondria, may have been exceedingly rare. Without mitochondria, the energy budget of eukaryotic cells would be insufficient to support the complexity that eventually led to multicellular life and intelligence. Every animal and plant on Earth exists because of this one ancient merger. The Cambrian explosion, approximately 540 million years ago, represents another potential filter point. Within a geologically brief period, complex multicellular animal life with hard body parts and eyes and predator-prey relationships appeared in the fossil record, following nearly 4 billion years of life remaining predominantly microbial. The trigger for this rapid diversification is still debated. Proposed causes include rising oxygen levels, a change in ocean chemistry, or ecological feedback dynamics. If the transition to complex animal life required specific conditions that are rare on other planets, then most life-bearing worlds may remain permanently microbial, simple but never complex, and certainly never intelligent. Intelligence itself may be a candidate for the Great Filter in our past. Of all the species that have ever existed on Earth, estimates range into the billions across deep time. Precisely one has developed the combination of cognition, social organization, language, and cumulative culture that leads to technology and science. Even among primates, our closest relatives, only humans made the transition. Chimpanzees are highly intelligent, socially complex, and capable of tool use, but have not developed anything resembling science or engineering. The step from high animal intelligence to technological civilization may require a very specific set of cognitive and social preconditions that were assembled on Earth by historical contingency and may not routinely assemble elsewhere. All of the above filters are in our past, which means, if any one of them is real, humanity is genuinely rare and perhaps special among the products of this universe. This is the optimistic interpretation of the Great Filter, but there is a deeply sobering alternative. The Great Filter may lie in our future. A civilization reaching the level of nuclear technology, biotechnology, artificial intelligence, and nanotechnology may routinely develop the tools of its own destruction before it has time to become a spacefaring species. A species that invents nuclear weapons, engineered pathogens, and misaligned artificial intelligence within a century of developing radio, as we have, may face catastrophic self-termination before it can establish the distributed presence that would make it detectable and permanent. The Mars and Enceladus argument for the great filter's location is particularly striking. If we discover simple microbial life on Mars, or in the ocean of Enceladus, or elsewhere in our own solar system, the discovery would be simultaneously one of the greatest scientific achievements in human history and one of the most terrifying. It would confirm that life arises easily given the right conditions, that abiogenesis is not an astronomically rare event. But if abiogenesis is easy, then the great filter cannot lie there. It must lie somewhere else, closer to or beyond where humanity currently stands. Life being common would mean that the silence requires some other explanation, and the explanations involving future catastrophe become more plausible. The anthropic shadow is a subtle effect that complicates our ability to reason about the great filter. If a civilization is destroyed by a catastrophe at some regular probability per century, then any observer who exists must be living before the catastrophe has yet occurred. The selection effect produced by our own existence biases us to underestimate the probability of extinction events that have not yet happened to us. This means we may systematically underestimate the probability of a future great filter, even if the evidence for it is present in our historical record. Correctly accounting for anthropic bias is one of the technically subtle aspects of reasoning about our long-term prospects as a species. There is one final observation about the great filter that Robin Hanson considered most important. The filter is not necessarily a single step. It may be a series of steps, each individually improbable, whose joint probability is very small. Perhaps abiogenesis is moderately rare, eukaryogenesis somewhat rarer, complex multicellularity rarer still, intelligence rarer again, and long-term technological civilization rarest of all. The cumulative probability of all these steps being traversed successfully could easily produce a galaxy in which we are among the only civilizations, without any one step being catastrophically improbable in isolation. The great filter may not be a wall but a long slope, each step moderately difficult, the full sequence extraordinarily so. Whether the filter is behind us or ahead of us is one of the most consequential, unanswered scientific questions of our time. If it is behind us, humanity has already cleared the hardest hurdle, and the future may be long and rich. If it is ahead, we are approaching the most dangerous period our species has ever faced, the period when our technology surpasses our wisdom. The answer matters not just philosophically, but practically. It should inform our priorities as a civilization. The search for life elsewhere in the universe is therefore not idle curiosity. It is an investigation into the nature of our own future. If the great filter lies neither clearly in our past nor clearly in our future, if we accept that life and even intelligence may be reasonably common, then the Fermi Paradox still demands an explanation. Why is the sky silent? Why have no civilizations contacted us? There are many proposed answers to this question that do not require civilizations to be rare or self-destructive. They require instead something about the nature of communication, or the nature of civilizations, or the nature of the universe itself that makes contact unlikely even between civilizations that exist and persist. These explanations sit in Brin's category 1. They exist, but we have not detected them, for reasons we have not yet understood. The most darkly compelling of these is what Chinese science fiction author Liu Cixin called the dark forest theory, described in his 2008 novel of the same name. The argument runs as follows. Every civilization needs resources to survive and expand. Resources in the universe are finite. A civilization cannot know the intentions of another civilization it encounters, and cannot trust what that civilization communicates. The cost of being wrong about a civilization's intentions, trusting one that is hostile, is extinction. The cost of being wrong in the other direction, destroying a peaceful civilization, is much lower. Given this asymmetry, the rational strategy for any civilization aware of another is to eliminate it before it grows powerful enough to pose a threat. The universe is therefore a dark forest in which every civilization hides and fires at anything it detects. The dark forest theory is logically coherent, and it has a disturbing implication for the SETI project. If the universe operates on dark forest principles, then broadcasting our location is one of the most dangerous things humanity could do. The Arecibo message of 1974, a binary encoded radio transmission sent toward the globular cluster Messier 13, would, in a dark forest universe, be a beacon announcing our coordinates to every hostile civilization within 25,000 light-years. The argument has led some researchers, including Stephen Hawking, to advocate strongly against active METI, messages to extraterrestrial intelligence, on the grounds that the risk of attracting attention from a hostile species far outweighs any scientific benefit. The METI debate in the SETI community remains active and unresolved. The zoo hypothesis, proposed by physicist John Ball in 1973, takes a different approach. It suggests that advanced civilizations know we are here, but have deliberately chosen not to contact us, either to allow our development to proceed without interference, analogous to a wildlife preserve or a zoo, or because they are following a policy of non-contact with civilizations below a certain level of development. In this scenario, the silence is not an absence of civilizations, but an active, maintained silence. The galaxy may be full of observers watching us from a respectful distance, waiting for us to reach some threshold, perhaps interstellar travel, perhaps a certain level of social or ethical development, before making contact. A related hypothesis is the planetarium hypothesis, proposed by science fiction writer and later physicist Stephen Baxter. In this scenario, we are living inside a simulation or a constructed environment designed to appear empty of other civilizations. Our observations of the universe are not observations of the real universe, but of a carefully constructed illusion maintained by our simulators. This is a version of the simulation hypothesis applied specifically to the Fermi Paradox. It is not falsifiable in any direct sense. Any observation we make could in principle be part of the simulation, which limits its scientific utility, but it is logically consistent with the evidence and cannot be dismissed on those grounds. The temporal mismatch hypothesis suggests that the silence is simply a matter of timing. The universe is 13.8 billion years old. Stars and planets have been forming for most of that time. But the conditions for complex life have not always existed everywhere. Heavy elements, carbon, oxygen, nitrogen, the building blocks of biochemistry, had to be forged in stellar interiors and distributed by supernovae before planets like Earth could form with the right chemistry. This process takes several stellar generations. Perhaps other civilizations did arise, but billions of years ago, before we existed to receive them. Or perhaps most civilizations will arise billions of years from now, when the universe is older and richer in heavy elements. We may simply be at an awkward point in cosmic history. Not the first, but not the majority. The Transcension Hypothesis, developed by futurist John Smart, proposes that as civilizations advance, they consistently direct their development inward rather than outward. Instead of expanding across space, a project requiring enormous energy and time, advanced civilizations compress their activity into smaller and smaller physical volumes, into ever denser computational substrates ultimately perhaps into something approaching the physical limits of matter. In this scenario, advanced civilizations are not spreading across the galaxy in ways we can detect. They are deepening their internal experience in ways we cannot. They disappear from the observable universe not because they are destroyed, but because they have moved to a scale of existence beyond our observational reach. The rare communication hypothesis simply notes that our assumption about how civilizations communicate may be wrong. We have been listening for radio waves and laser pulses for 60 years because those are the forms of communication we developed first. But a civilization 10,000 years more advanced than us might communicate in ways we have not imagined. Perhaps they use modulated neutrino beams. Perhaps they use gravitational wave pulses. Perhaps they communicate through changes in quantum states at a distance. Perhaps they have moved entirely beyond electromagnetic communication because something better exists. We may be listening at the wrong frequency in the most literal possible sense. Not the wrong radio frequency, but the wrong physical phenomenon entirely. The Gaian bottleneck hypothesis, proposed by astrobiologists Charles Lineweaver and Aditya Chopra in 2012, adds a biological dimension to the filter discussion. They argue that the habitability of a planet is not a static property, but a dynamic one that requires active maintenance by life itself. Early life must regulate a planet's temperature, atmosphere, and chemistry quickly enough to prevent runaway warming or cooling as the host star brightens. Most planets fail this regulation challenge and become sterile before complex life can arise. A kind of fast filter that eliminates most candidates in the first billion years. The Earth may have been uniquely successful at this self-regulation through the early activity of microbial life, and the same success may be rare. The sheer diversity of proposed solutions to the Fermi Paradox is itself informative. The fact that so many different hypotheses, ranging from civilizations being rare to civilizations being hidden, to civilizations being beyond our comprehension, are all consistent with the observational evidence suggests that our current evidence is genuinely insufficient to distinguish between them. We need more data. The most impactful data point would be the detection of a second origin of life anywhere in the solar system, which would dramatically constrain the abiogenesis probability. The second most impactful would be the detection of a biosignature, signs of life in the atmosphere of an exoplanet, by the James Webb Space Telescope or its successors. Any of these findings would immediately eliminate some hypotheses and strengthen others. Each of the hypotheses in this chapter says something different about the nature of civilizations and their choices. The Dark Forest says civilizations are rational and ruthless. The Zoo says they are wise and restrained. The Transcension says they are inward-looking and ultimately indifferent to expansion. The temporal mismatch says we are early rather than rare. None of these is falsified by current evidence. All of them live in the space of the silence. In the next two chapters, we shift from what other civilizations might be doing to what makes our own existence here, on this planet, possible at all, and whether the conditions that produced us are common or extraordinary. In 2004, paleontologist Peter Ward and astronomer Donald Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was a systematic challenge to the assumption that Earth is a typical planet, and that the evolution of complex life here is therefore representative of what happens everywhere given enough time. Ward and Brownlee argued instead that Earth is extraordinarily unusual, not just in one or two respects, but in a remarkable conjunction of many independent factors, each of which appears necessary for the development of complex life. Any one of these factors being absent might have prevented multicellular life from arising at all. Together, they make Earth something close to a cosmic accident. The first factor is the galactic habitable zone. Not all parts of the Milky Way are equally hospitable to complex life. The galactic center is a violent environment. Dense stellar populations produce frequent supernovae. The radiation environment is intense, and the close proximity of stars increases the risk of gravitational perturbations to planetary orbits. The outer galaxy is quieter but has low metallicity. Fewer heavy elements to build rocky planets and organic molecules. The region of the galaxy that is old enough, metal-rich enough, and stable enough for a planet like Earth to form and persist for several billion years is a relatively narrow ring. Earth sits within this ring. Planets at other galactic radii may be too irradiated, too disrupted, or too chemically impoverished for complex life. The second factor is the role of Jupiter. Our solar system's largest planet, with a mass greater than all other planets combined, sits in an orbit that sweeps up comets and asteroids that might otherwise bombard the inner planets continuously. Jupiter acts as a gravitational shield, deflecting and absorbing much of the debris that would otherwise pepper Earth with large impacts. The late heavy bombardment, approximately 3.9 billion years ago, occurred despite Jupiter's presence, suggesting its shielding effect is imperfect. But without Jupiter, the impact rate on Earth throughout its history might have been so high that complex life would have been repeatedly reset before it could develop beyond microbial stages. Not all solar systems have a Jupiter-like protector in the right orbit. The Moon provides a third unusual feature. Our Moon is exceptionally large relative to Earth, larger by comparison than the Moon of any other rocky planet in the solar system. The gravitational interaction of this large Moon stabilizes Earth's axial tilt. The tilt of Earth's rotational axis relative to its orbit, currently about 23.4 degrees, determines the seasons and strongly influences global climate. Without the Moon's stabilizing influence, computer models show that Earth's axial tilt could vary chaotically between near zero and greater than 80 degrees on million-year timescales, producing extreme climate swings that might prevent the sustained stable environment necessary for the evolution of complex land-based life. Most rocky planets do not have large moons. Plate tectonics is another apparently unusual feature of Earth that may be necessary for complex life. The motion of tectonic plates cycles carbon dioxide between the atmosphere and the mantle through volcanic outgassing and subduction of carbonate rocks. This carbonate-silicate cycle acts as a thermostat. When the planet warms, weathering of silicate rocks draws down atmospheric carbon dioxide, cooling the planet. When the planet cools, reduced weathering allows carbon dioxide to accumulate from volcanoes, warming the planet again. This stabilizing feedback operates over millions of years and has kept Earth's surface habitable through changes in solar luminosity and other perturbations. Venus and Mars appear to lack active plate tectonics, and both are now uninhabitable. Whether Earth-style plate tectonics is common on rocky planets is uncertain. The host star type is also significant. The Sun is a G-type main sequence star, middling in size, temperature, and luminosity. The most common type of star in the galaxy is the M dwarf, or red dwarf, smaller, cooler, and much longer lived than the Sun. Red dwarfs are appealing hosts for habitable planets in principle. They last for trillions of years, far outlasting any G-type star. But planets in the habitable zone of a red dwarf are necessarily very close to the star, and at that proximity they are subject to tidal locking. One hemisphere permanently facing the star, the other in eternal night. They are also exposed to intense flare activity that can strip planetary atmospheres over geological time. Whether life can thrive on tidally locked planets around, flaring red dwarfs is an open and vigorously debated question in astrobiology. The timing of the Cambrian explosion, the rapid diversification of complex animal life 540 million years ago, may also reflect conditions specific to Earth's history. The explosion appears to coincide with significant changes in ocean chemistry, particularly rising oxygen and phosphate levels, that provided new biochemical possibilities. The oxygenation of Earth's atmosphere, driven by photosynthetic cyanobacteria, beginning around 2.4 billion years ago in the Great Oxidation Event, was a prerequisite for the high-energy metabolism that complex animals require. The timing and progression of atmospheric oxygenation depended on a specific geological and biological history that may not be reproduced on other planets even if they host microbial life. Ward and Brownlee's conclusion was that complex multicellular life, animals, in particular, is rare in the universe, even if microbial life is common. Simple life may be widespread. Complex life may be exceptional. This would resolve the Fermi paradox in a straightforward way. The FL term in the Drake equation might be close to 1. Life arises easily. But the terms for complex life and intelligence are very small. The galaxy might be full of bacteria-equivalent organisms on billions of planets, none of which ever produced anything capable of building a radio telescope. The universe may be teeming with life in the broadest sense and empty of consciousness in any recognizable form. The rare Earth hypothesis is not without critics. Some astrobiologists argue that Ward and Brownlee overstate the case for Earth's uniqueness, that alternative biochemical pathways and planetary configurations can achieve similar outcomes, and that life is more adaptable than the hypothesis assumes. The discovery of extremophiles, organisms thriving in boiling hydrothermal vents, deep rock, highly acidic lakes, and the intensely cold and dry Antarctic, has demonstrated that life on Earth occupies a much wider range of environments than previously thought, suggesting that the conditions needed for life might be more flexible than rare Earth implies. The debate between rare Earth proponents and those who believe complex life is common remains scientifically unresolved. What the rare Earth hypothesis provides, regardless of whether all its specific claims survive scrutiny, is a sobering reframing of the question. Instead of asking why other civilizations haven't contacted us, it asks us to consider whether there were other civilizations to do the contacting. Instead of a universe full of quiet observers, it pictures a universe in which the emergence of a species that can ask questions about the universe is an extraordinarily improbable achievement. If that is true, then the Fermi paradox resolves not because of filters or silence or hiding, but because the chain of events that led from the Big Bang to the moment Fermi asked his question at lunch was extraordinarily long, contingent and fragile, and mostly fails on almost every planet before it gets anywhere near producing someone to ask the question. Whether life is rare or common, whether Earth is typical or exceptional, is ultimately an empirical question. We will answer it not through philosophical argument, but through observation, by detecting or not detecting biosignatures in the atmospheres of rocky exoplanets, by finding or not finding life elsewhere in our own solar system, by accumulating more of the data that only the universe can provide. The beautiful answer to the Fermi paradox, the one promised in the title, does not require us to know whether we are alone. It requires only that we sit with the question honestly. That is the subject of the next chapter. I want to be direct with you about what I mean by a beautiful answer. I do not mean a comforting answer. Some of what I'm about to say is sobering. I mean an answer that, when you understand it fully and sit with it honestly, produces something that feels like wonder rather than despair. Even though the content is the recognition that we may be profoundly alone, the beautiful answer to the Fermi paradox is not a solution. It is a reframing. It is an understanding of what the silence means, not only in the context of the search for other civilizations, but in the context of what it means to be the kind of creature that asks the question at all. It begins with scale. The universe is 13.8 billion years old. You have existed for, at most, a few decades. Your species has existed for about 300,000 years. Civilization, in the sense of writing and cities and accumulating knowledge across generations, has existed for about 10,000 years. Science, in the sense of systematic empirical investigation of reality, has existed for about 400 years. In all of that time, the universe has been doing what it does, forming stars, exploding supernova, building galaxies, allowing chemistry to organize and reorganize on the surfaces of planets, without reference to whether anyone was watching. And then, in an extraordinarily brief moment on the scale of cosmic time, on one planet, matter arranged itself into something capable of looking back. Carl Sagan expressed this idea more beautifully than anyone. We are a way for the cosmos to know itself. The atoms in your body were forged in stellar interiors across billions of years of nucleosynthesis. The carbon in your cells was fused in stars that died before the solar system formed. The iron in your blood came from supernovae. You are literally made of ancient stars. And more than that, you are the configuration of those ancient stars that has become capable of understanding where it came from. The universe did not simply produce you, it produced in you the capacity to comprehend itself. That is not a small thing. Whatever the answer to the Fermi paradox, that fact stands. The astronomer David Grinspoon, in his book Earth in Human Hands, argues for what he calls cosmic adulthood. The idea that a species becomes truly mature when it understands its place in the cosmos and takes responsibility for what that understanding implies. In Grinspoon's view, the Fermi paradox is not primarily a question about other civilizations. It is a question about us. Are we a species that will destroy itself in the manner that the Great Filter's future location implies? Or are we a species that will develop the wisdom to match our technology and join the long-lived intelligences that presumably populate a universe where the filter is behind most civilizations? The answer depends on choices we make in the next few centuries. There is a reading of the Fermi paradox that I find genuinely moving. If we are among the only self-aware beings in the Milky Way, or in a much larger volume, then the silence is not an absence, but a presence. It is the presence of all the universe's potential for consciousness, concentrated in the handful of places where the improbable chain of events ran all the way to completion. Every thought you have, every question you ask, every piece of music you have ever heard, every experience of beauty or connection, these things are the universe's way of experiencing itself. And if such experiences are rare on cosmic scales, they are correspondingly precious. The silence around us is not emptiness. It is the rest of the universe, waiting. The overview effect is a term coined by philosopher and author Frank White for the cognitive shift reported by virtually every astronaut who has seen Earth from space. The view of the planet from orbit, small, fragile, achingly beautiful, surrounded by absolute darkness, produces a visceral understanding of unity and fragility that is difficult to convey in words, but consistently described as transformative. The Fermi paradox offers something analogous, an intellectual overview effect. When you understand the full scale of the question, the age of the universe, the number of candidate worlds, the improbability of what happened here, the silence of all that vast space, you come back to Earth differently. The light that reaches your eyes from the sky at night carries information about what is not out there, and that information changes the meaning of being. Here, the philosopher Nick Bostrom argued that the worst-case scenario for the Fermi Paradox is finding microbial life on Mars. If life arose independently twice in the solar system, the filter is almost certainly ahead of us. But the best-case scenario, Bostrom suggested, is that we are alone in the entire observable universe, because it means the filter is behind us and the future is open. I think there is something right in this framing, but something incomplete. The most beautiful answer does not require us to be alone. It requires us to understand that regardless of what is out there, we are here, conscious, curious, capable of science and art and love, and the kind of thought that asks, where is everybody? That is extraordinary under any interpretation. There is something specifically right about encountering this question before sleep. Sleep is the daily reminder that consciousness is not a permanent condition. It is a temporary and fragile configuration of matter that can be interrupted. We spend roughly a third of our lives in unconscious rest, and we emerge from it each morning as if recovering from a small oblivion. The Fermi Paradox asks a similar question on a cosmic scale. How common is the configuration of matter that becomes aware of itself? If the answer is very rare, then each moment of wakefulness is correspondingly precious. If the answer is common, then consciousness is woven through the fabric of the cosmos in ways we have not yet detected. Both answers, honestly held, produce the same response in me: gratitude for being here at all. The beautiful answer is not that other civilizations exist and we will find them. It is not that we are alone and the universe is ours. It is simpler and stranger than either. The beautiful answer is the question itself. The fact that the universe has, at least here and at least now, arranged itself into something capable of wondering about its own loneliness. The Fermi Paradox is the universe looking at itself and asking, is anyone else out there? That question is an answer. It is the answer to what consciousness is for. It is the most improbable thing this particular collection of ancient stellar matter has ever done, and you are here for it. The philosopher Thomas Nagel asked in a famous 1974 paper what it is like to be a bat. His point was that consciousness involves a subjective, first-person quality of experience, what it is like to be a particular kind of mind that cannot be fully captured by third-person scientific description. The Fermi Paradox adds a dimension to this question. We know what it is like to be the kind of mind that wonders about the universe, because we are such minds. What we do not know is whether the universe contains other kinds of minds with their own characteristic experiences of wonder, or whether our particular kind of wondering is the only kind that has ever existed. That question cannot be answered by radio telescopes alone. It may require a much deeper understanding of what minds are and why they arise. The silence also offers a quieter kind of beauty, the beauty of not knowing. We live in an era of rapid information accumulation, in which uncertainty is often experienced as a temporary problem to be solved, rather than a permanent feature of honest inquiry. The Fermi Paradox is one of the places where the universe refuses to resolve. We have been asking the question seriously for 65 years and the answer has not come. It may not come in the next 65 years. It may come tomorrow. The uncertainty is not a failure of science. It is science working honestly at the edge of what is knowable. There is a particular quality of rest available to a mind that can sit at that edge without forcing a resolution. And I think it is available to you right now. Rest in that for a moment. You are the universe asking, where is everybody? Whatever else is true, whether the galaxy is empty or full of hidden civilizations, you are the thing that got to ask. That is not a small thing. In the largest view of all, it may be the only thing that matters. And it is enough, more than enough, to settle into for the night. The search for extraterrestrial life is undergoing its most significant methodological expansion since Frank Drake pointed a telescope at Tau Ceti in 1960. For most of SETI's history, the search was synonymous with radio astronomy, listening for narrowband signals at specific frequencies. In the past decade, the field has broadened into a systematic science of technosignatures and biosignatures that encompasses optical, infrared, ultraviolet, and X-ray wavelengths, as well as the search for chemical and physical signatures of life and technology in the spectra of exoplanet atmospheres and in the thermodynamic properties of entire star systems. The distinction between SETI, search for extraterrestrial intelligence, and astrobiology, the search for life in any form, has become increasingly blurred, and the tools of both disciplines are converging. Breakthrough. Listen, the 10-year $100 million initiative, launched in 2015, has published its data openly and produced the most comprehensive public radio SETI dataset in history. As of its most recent published results, it has surveyed approximately 1 million nearby stars across a wide range of radio frequencies, listened to 100 nearby galaxies, and monitored significant portions of the galactic plane. Machine learning algorithms have been applied to the data to search for narrowband signals, broadband pulses, and other anomalies that might indicate artificial origin. Everything found so far has a natural explanation or has been identified as human-made interference. The initiative continues its survey and is expanding its frequency coverage and its list of target stars. The James Webb Space Telescope, launched in December 2021, opened a new front in the search for life by providing, for the first time, the sensitivity needed to analyze the atmospheric composition of rocky planets in the habitable zones of nearby stars. The technique is transmission spectroscopy. When a planet transits its host star, the starlight passes through the planet's atmosphere, and different molecules absorb light at specific wavelengths, leaving characteristic signatures in the spectrum. Webb has already detected carbon dioxide and methane in the atmospheres of gas giant exoplanets. The detection of oxygen, ozone, nitrous oxide, or chloromethane in the atmosphere of a rocky exoplanet would be highly significant. These molecules are produced by biological processes on Earth and are difficult to generate in large quantities through purely geological chemistry. The TRAPPIST-1 system, discovered in 2017, is one of the most intensively studied targets for biosignature detection. It consists of 7 rocky planets orbiting a red dwarf star approximately 40 light-years from Earth. 3 of the planets, TRAPPIST-1e, F, and G, orbit within the habitable zone. The planets are close enough that their atmospheric spectra are in principle detectable with James Webb. Early results from Webb observations of TRAPPIST-1b and C have been published, ruling out the presence of thick carbon dioxide atmospheres for these inner planets, which suggests they may be dry and rocky like Venus. The potentially habitable outer planets remain under active observation. Technosignature science is expanding beyond radio signals into a broader search for physical effects of technology on planetary or stellar systems. Atmospheric technosignatures include the presence of industrial pollutants. Nitrogen dioxide and chlorofluorocarbons are produced by industrial processes on Earth and have no known natural source at high concentrations. Detecting these in an exoplanet's atmosphere would require a large quantity of the compound and a very sensitive spectrograph, but is not physically impossible with near-future instruments. Other proposed technosignatures include the optical laser equivalent of radio signals, the waste heat signature of a planet with extensive artificial energy generation, and the gravitational wave signature of very large engineered structures. The search for Dyson spheres and other megastructures has advanced significantly, with the availability of large infrared and optical survey datasets. A fully enclosed Dyson sphere would convert the entire output of its host star from visible light into infrared heat, making the star invisible in optical surveys while producing a distinctive thermal signal in infrared. Partial Dyson structures, Dyson swarms for example, might produce intermediate infrared excesses. Systematic surveys of infrared catalogues from the WISE and Spitzer missions have identified candidate objects with anomalous infrared properties, but all examined in detail have received natural explanations including circumstellar dust disks, binary star systems, and background galaxy contamination. The search continues as survey sensitivity and coverage improve. The Allen Telescope Array in Northern California, built specifically for SETI observations and operated by the SETI Institute, is currently undergoing a major upgrade known as the Hat Creek Radio Observatory Collaboratory. The upgrade will expand the number of antennas from 42 to 350, dramatically increasing the array's collecting area and sensitivity. The upgraded array will be capable of conducting simultaneous SETI observations across a very wide field of view, monitoring millions of stars in the directions they are pointing while conducting conventional radio astronomy. Commensal observing, using the same telescope time for both SETI and conventional astronomy, maximizes the scientific output of each observation and represents a growing trend in the field. The debate over whether humanity should actively transmit signals toward other stars, METI, messaging extraterrestrial intelligence, continues to divide the SETI community. Proponents argue that if every civilization is simply listening without transmitting, the galaxy will remain permanently silent by collective inaction, a cosmic standoff. The way to break the standoff is for some civilization to begin transmitting, and that civilization might as well be us. Opponents, including a group of scientists who published a formal declaration in 2015, calling for an international discussion before any further intentional transmissions, argue that the risks of attracting attention from a potentially hostile advanced civilization are unknown and potentially catastrophic. No international governance framework for METI currently exists. The next 20 years are likely to be the most decisive in the history of the search for extraterrestrial life. James Webb observations of dozens of habitable zone rocky planets will either detect biosignature candidates or establish strong upper limits on the prevalence of life-bearing atmospheres. The planned successors to Webb, including the Habitable Worlds Observatory proposed in the 2030 Decadal Survey, would directly image Earth-like planets and analyze their spectra with higher sensitivity. LISA will begin observations of the gravitational wave sky in the millihertz band, potentially detecting signatures that only advanced engineering could produce. Pulsar timing arrays will continue to build the low-frequency gravitational wave background dataset, and artificial intelligence will be applied to all of these datasets with a power and comprehensiveness that no human team could replicate. Within a generation, we may know whether we are alone. Whether or not the search finds something, it is changing us. The act of searching, of taking the questions seriously, of building instruments and writing equations and spending careers on the possibility, is itself a form of civilizational maturity. The cultures that search for other minds in the universe are cultures that have looked outward beyond their own immediate concerns and recognized that the question of life's place in the cosmos is the largest question available to them. Whatever the answer turns out to be, the search is worth conducting. Because a species that does not ask where is everybody is a species that has not yet fully understood where it is. Enrico Fermi asked his question at lunch in 1950 and died 4 years later in 1954 of stomach cancer. He never heard a signal from another civilization. He never expected to. He asked the question with the casual confidence of a physicist who understands that the most useful questions are often the ones that expose a contradiction. Not because the contradiction resolves easily, but because sitting with it honestly is how understanding deepens. He posed the question and left it. The question has been sitting on a table ever since, waiting for someone to answer it. It is still waiting. We know considerably more now than Fermi did in 1950. We know that the universe contains trillions of galaxies, each with hundreds of billions of stars, and that virtually all of those stars have planets. We know that the chemistry of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, is distributed across the galaxy by stellar evolution and is not special to our solar system. We know that the habitable zone is a concept that applies to billions of planets. We know that extremophiles on Earth can survive conditions far harsher than previously thought possible, extending the range of environments where life might exist. We have found amino acids in meteorites, water in comets, complex organic molecules in the interstellar medium. The building blocks of life are everywhere. Life itself, so far as we can tell, is not. The silence is data. I want to say that one more time, because it is easy to receive it as an absence rather than a presence. The silence is data. It tells us something real about the universe. It constrains the space of possible answers. It does not tell us that we are definitely alone. The search is too young and too incomplete for that conclusion. But it tells us that if other civilizations exist and have existed, they are not filling the galaxy with obvious signals. They are not building megastructures detectable in infrared surveys. They are not visiting us or leaving artifacts we have found. Whatever is true about the universe, those constraints are real and must be incorporated into any honest answer. The question I find most worth sitting with at the end of all this is not whether other civilizations exist, it is what it would mean if they do not. If the great filter lies behind us, if the improbable steps were abiogenesis and eukaryogenesis, and the Cambrian explosion and the emergence of human-level cognition, then we are the inheritors of an extraordinarily unlikely sequence of events, each of which could have gone differently and did not. We are not the inevitable product of a universe friendly to intelligence. We are the improbable product of a universe indifferent to intelligence, in which the right conditions and the right accidents happen to accumulate in one particular place over 4 billion years. And we are, perhaps, alone in a galaxy of 300 billion stars to appreciate that. That aloneness, if it is real, is not a wound. It is a weight, the kind of weight that, when you accept it fully, changes what you do with your time. If we are rare, then what we do here matters in a way that would not be true in a universe teeming with conscious observers. If we are the only thing in this part of the galaxy that cares about beauty, that formulates ethics, that builds science and art and music and asks questions about its own existence, then the continuation of that project is cosmically important in a very literal sense. We are not just one civilization among many. We may be the only stewards of consciousness within reach of each other. That is a reason to be careful with what we have built. There is a particular quality to the night sky that I think the Fermi Paradox reveals more clearly than anything else. Every point of light you see is a star. Most of those stars have planets. Some of those planets are in habitable zones. And yet, as far as we can tell, the light from none of them carries an intentional message. None of them is surrounded by a megastructure. None of them has been transformed by engineering. The stars are doing what they have always done, fusing hydrogen, producing light, living their stellar lifetimes, dying, without reference to whether anyone finds them meaningful. The meaning is ours. We brought it. We may be the only ones who brought it to this corner of the universe, at this moment in cosmic time. The astronomer Carl Sagan spent his career trying to communicate the scale and age of the universe to people who had not chosen to be scientists. He believed, and I think rightly, that understanding the cosmos changes a person in a specific way. It makes them simultaneously more humble about their own importance and more astonished at the improbability of their existence. His pale blue dot image, the photograph of Earth taken by the Voyager 1 spacecraft from beyond the orbit of Neptune in 1990, shows Earth as a fraction of a pixel in a vast, dark, empty frame. The silence in that image is the same silence the Fermi Paradox points at. It is not the silence of emptiness waiting to be filled. It is the silence of scale. The honest silence of a universe that is exactly as large as it is and contains exactly as much consciousness as it contains, which may be very little concentrated here for a brief time, asking enormous questions. Before sleep is one of the few times in daily life when the scale of the universe becomes genuinely accessible to the mind. The obligations and demands of waking life occupy a very small spatial and temporal scale. This room, this building, this city, this year. In the quiet before sleep, those scales relax. The mind can hold larger things, the 13.8 billion years, the 2 trillion galaxies, the silence, the question, and if you sit with the silence long enough, without rushing to a resolution, something interesting happens. The silence stops feeling like an absence and starts feeling like a space that is full of something that is not sound and not emptiness, but something between them. The space in which the universe exists, and in which, for this brief and improbable moment, you are conscious within it. There is a practice in contemplative traditions of sitting with a question rather than rushing to an answer, allowing the question itself to do work in the mind, opening up space that a premature answer would have closed. The Fermi Paradox is that kind of question. If you answer it too quickly, we are alone, or we are not alone, or we will find out eventually, you foreclose the more interesting experience of actually holding the uncertainty. The universe has been running for 13.8 billion years. Whatever the truth turns out to be about other minds in it, you have tonight and the night sky and the knowledge of how vast and old the cosmos is. That is already more than most arrangements of matter in the universe can claim. I want to say something about what the silence actually feels like when you encounter it honestly, not as an abstract scientific fact, not as a statistic about the number of stars surveyed and signals not found, but as an experience. The night sky, which looks so full of light to the naked eye, is almost entirely empty. The nearest star to the sun is 4.2 light-years away. Between here and there is nothing. No radio signals we have found, no artifacts, no visitors, just the distance, and the time it would take to cross it, and the silence that has occupied that distance for billions of years. When you let that settle in, not as a number, but as a feeling, it has a quality that is hard to name. It is not quite loneliness. It is more like standing in a very large room and realizing the room is bigger than you thought, and quiet in a way you had not expected, and that the quietness is real. Fermi asked, "Where is everybody?" The honest answer, 76 years later, is, we do not know. The beautiful answer, which is different from the honest one but not less true, is, here. We are here. Whoever else may or may not be out there, The one confirmed case of the universe producing something capable of asking the question is here, on this planet. Reading these words, lying in this bed, with this brief and extraordinary consciousness that will rest now and resume tomorrow, that is the beautiful answer. Not a destination reached, not a contact made. The universe, in this one location, listening to itself, that is enough. More than enough. Sleep well.